going to talk about net ionic equations and oxidation-reduction reactions. So what is a net ionic equation? A net ionic equation is an equation that you have with lots of other elements and compounds in it. And there are only a few elements and compounds that actually determine whether the reaction is going to take place. And the way you actually determine which elements or which compounds are the most important part of that equation is by doing a net ionic equation to it. So what you do is you actually start off by breaking the equation, and you need to find the drivers of the reaction. If you're confused on what drivers are, then drivers are the ones that cause the reaction. They are the cause of it. Okay? Oops. Hopefully you can see that. Okay. So they are the cause of the reaction. So you're actually looking at which compounds and which elements are actually causing the reaction. So most of your net ionic equations will be single and double displacement reactions. Okay? And what it is that sometimes you have chemical species that are involved in a reaction. And not all chemical species tend to be involved in the reaction. Some chemical species are just there, and they're just there to watch and observe how the reaction is taking place. So we call these spectators. And the spectators are the ones in our net ionic equation that we are going to eliminate. Okay? The actual drivers are actually the participants in the reaction. These are the drivers, or the ones that are causing the reaction. Okay? And these participants that are in the reaction start off as one compound, but as they go through the entire reaction, they eventually turn into some other new compound. And the compound has either ionic or covalent bonds. It doesn't really make a difference. Okay? And all of this is accomplished by losing or gaining electrons in the reaction. So in order to have a net ionic equation, your reaction must always be aqueous. Okay? And underline that. And when I say aqueous, I mean that with the benefits of having an aqueous reaction is that you can break it up into positive and negative charges. You do not break up your reaction if your state of matter for your compound or your element is a solid, liquid, or gas. Then you just keep it as it is. So in general, the spectators are the ones that are eliminated, and there are soluble ions that are unchanged. So the spectators are the ones that are eliminated, but that's because they don't change in the reaction at all. They are the exact same in the reactant as well as on the product side. Okay? So the example that I'm going to do for you today is actually a part of your notes, and it is double displacement reaction number 1. And this is the one where you form the precipitate, okay, or PPT. Okay? So we're going to be using our solubility chart to look at this. Okay? All right. So the first thing we're going to do is we are going to write a balanced equation. So go ahead and write balanced equation. And this is how I want you to break it down on the test also. So this is your BE. Okay? So we wrote our balanced equation. That's our BE. So the equation that I'm taking is from your own notes, from the double displacement reaction notes, and it is reaction number 1 where you formed a precipitate. So in that equation, we had PB2 acetate. So go ahead and write the equation for PB2 acetate. And when you use your solubility chart, which is right here, remember you're using your solubility chart. So we're looking up acetate right here. We'll look up acetate on our chart. It is right here. And acetate, when it reacts to any positive ion except silver and mercurous. Well, my acetate is reacting to lead, so it's soluble, okay? So it will be aqueous, or AQ for solubility. Reacts with ammonium phosphate. Okay, and go ahead and write that. When you use your solubility chart, that is also aqueous, will produce, and now remember that your positive charge will react with the negative charge on the other compound, and your positive charge of the other compound will react with the negative charge of the first compound. So when you do, you get lead 3 phosphate. Okay, lead 2 phosphate. Okay, so you get lead 2 phosphate, and when you use your solubility chart, you're looking at phosphate right here. So when you have phosphate in your solubility chart, it reacts to lead, which is not an alkaline ion, nor is it ammonium, is any other positive ion, so it's not soluble. So in this case, it is a solid, and reacting with ammonium acetate. And when you look that up on your, let me make this smaller. There you go. Should be able to see it now. Okay. And when you look up ammonium acetate in your solubility chart, it should say that it is aqueous. Okay. So this is ammonium acetate. So we can go ahead and balance this out. And when you balance this out, this is 3, this is 2, 1, and then 6. So that's balancing it out. The next thing we're going to do in order to figure out which compound and which element are the most important that are causing this reaction to move forward, we're going to now write the complete ionic equation, and which is CIE. So when we do ionic, I mean that it has a positive and it has a negative charge to it. So when I do, now I start breaking things down. And this is going to be, there's a couple of things that you have to remember when you're breaking it down. If you have a coefficient in front, keep in mind that this coefficient will be distributed to every single element and polyatomic ion, to every single one individually. And if you have a subscript at the bottom, remember that subscript applies to what's inside the parentheses or the elements that it is the subscript to. So in this case, when we have lead, we have just 3 lead, and the charge of lead, remember, is 2, so it's a 2+. And if you can't remember how I got the charge of lead, go back the old-fashioned way of doing this, where you have Pb(C2H3O2) with a 2 outside. Remember, this is an ionic equation, so the overall charge is 0. Acetate has a -1 charge. We don't know what the charge of lead is, so we're going to put an X, but we do know that there's only 1 atom of lead, and then there are 2 atoms of acetate. Looking at this equation, we can definitely say that the overall charge for lead is 2+. Okay, so that's where I got my 2+ here. And of course, this lead is aqueous, so I'm going to write AQ. I'm going to bring up the acetate. Now, this acetate is there are 2 acetate ions, but those 2 times 3 would give you a total of 6 acetate ions. Okay, and that is, of course, also aqueous. This is aqueous, so we can break it down. And so this 2 will apply to ammonium, but you've already had 3 ammonium ions, and then you have 2 of those ammonium ions of the 3, so that makes it a total of 6 ammonium ions. And each one is aqueous. Okay, and then we have 2 phosphate. 2 phosphate ions that are aqueous. And then, of course, we have this as our solid. Since this is a solid, we're going to keep it as it is. We are not going to break it up. And, of course, since this is aqueous, we are going to break it up. This 6 will apply not only to the ammonium, but this 6 will also apply to the acetate. So now we have 6 ammonium, which is aqueous, plus 6 acetate, which is also aqueous. And remember, acetate has a -1 charge. So this is the equation we have. And if you start looking at this, we want to, first of all, see what is not being changed. We want to find our spectator ions. And remember, your spectator ions are the ones that are not changed. They're unchanged. So the spectator ions should not only, the spectator ions need to have 3 things in common. One is they need to have the same number of coefficient or ions, they need to have the same charge, and they need to have the same state of matter. Okay, so if all 3 match, then you can cancel that element or compound out, that element or ion out on the reactant as well as the product side. Okay, so we have 3 Pb2 plus aqueous, and I don't see where 3 Pb2 plus, that's aqueous, is located here. So I'm going to say that this is not a spectator. Then I have 6 acetate, that's aqueous. And go here, and wow, what do you know? 6 acetate, that is aqueous. So these are both, they have in common, so we can actually just cross them out like that. Then we have 6 ammonium plus acetate. And on the other side, the product, I also have 6 ammonium positive plus 1 charge, that's aqueous. So I have that out. I'm going to cancel that. And everything else that's there, I cannot cancel anymore. So now I'm going to write my Net Ionic Equation. Or NIE. Okay. So my Net Ionic Equation is everything that is left over. So just go ahead and copy that down. So it'd be 3 Pb2 ions that are going to react with 2 phosphates, and that's aqueous, to produce our solid, which is right here, Pb3 phosphate, which is a solid. Notice that whatever you have in the reactant will make up your product that is left over. You don't have anything extra. So this right here is what's causing the reaction to occur. If we didn't have lead and we didn't have phosphate in this reaction, your reaction would not occur and none of this would be formed. So that's our Net Ionic Equation that I have. Let's go ahead and talk about oxidation-reduction equations. First of all, oxidation-reduction, these are also called redox. Okay, they're also called redox. And in this case, we just want to know where those electrons are moving, where they're coming from, and where they are going. So the most common form of this is usually we talk about these kind of reactions when we are talking about batteries. Okay. So what happens is that these reactions are actually involved in the transfer of electrons. And when these reactions involve the transfer of electrons, we say that it is oxidation or redox reactions that are occurring. Okay, so when you have reduction, you have when an element gains electrons, its positive charge is reduced. What that means that its positive charge is reduced is that it becomes more negative. So if you have a number line, right? And if you have a number line and you're at 0, and let's say you are at 1 plus. If you're going from 1 plus to 0, you're becoming less positive, right? So you're becoming more negative, which means you're gaining electrons. So you're going this way, where you are becoming more negative, okay? Oxidation is when an element loses electrons. So in this case, the electron is becoming more positive. That means that if you have a number line right here, and 0 is right here, and you have +1, and you're going from 0 now to +1. Or you can go from -2 to -1. Either way, now you are moving on this side on this side of the number line, you are becoming more positive. So that is the loss of electrons in this case. If you have a hard time remembering this, you can remember oil rig. And oil rig is oxidation is loss of electrons. So OIL, that's oil. And then rig, reduction is gain, RIG. Reduction is gain of electrons. Okay? If that doesn't work for you, then try the mnemonic Leo says grr. Loss of electrons is oxidation and gain of electrons is reduction. If that doesn't work for you either, then I've got one more where the oxidation has an X, and what you can do is you can turn this X around and make it into a positive sign to remind you that it is the loss of electrons. It becomes positive. Okay, if that helps you at all. Okay, so moving on. Now, when we are doing oxidation and reduction reactions, we do the exact same thing as we did before. We label our balanced equation, our common ionic, complete ionic equation, and the net ionic equation. So usually the reactions that we have for this are your typically synthesis reactions, are single displacement reactions, but synthesis can also do it. So both synthesis, single displacement reaction, and even decomposition can be redox reactions. What cannot be redox reactions are anything that's a double displacement, cannot, and combustion cannot be a redox reaction. Okay, so they cannot be it. So my example to you is, let's say the balanced equation that we have this time is, let's say you have zinc, solid, that reacts with 2HCl, which of course this is an acid, so it is aqueous, will produce zinc chloride, which is of course aqueous, and hydrogen gas. Okay, that will produce hydrogen gas. So this is our reaction that we have. It's got the states of matter. It is completely balanced. So now we're going to do the complete ionic equation. And when we do the complete ionic equation, keep in mind that we are breaking everything up into plus and minus charges. The only thing that we can break up into plus and minus charges are your aqueous solutions. Anything that's a solid, liquid, or gas stays as it is, and you do not, in any circumstances, break it up. You want to also write in there, right here off to the side, is that if an element is by itself in a reaction, then that element has a charge of 0. Okay, has a charge of 0. So in this case, we have zinc here. Zinc is by itself. So in this case, zinc, since it's not linked to any other element, it will have a charge of 0, and it's a solid. The hydrogen and the chlorine are in a bond together, so remember that this 2 gets distributed within, just like we did for the complete ionic equation for the hydrogen and chlorine. So it'd be 2 hydrogen with a +1 charge, aqueous, and 2 chlorine that have a -1 charge, and it is aqueous. Produces zinc chloride. Remember, zinc chloride, zinc has a 2+ charge, and it's aqueous. And in this case, look at this. This chlorine right here has, there are 2 chlorine ions, so don't forget to put that 2 in front. 2 chlorine. Each one has a -1 charge, and it is aqueous. Plus 2 gas. And if an element is by itself in a reaction, then that element has a charge of 0, so this hydrogen will have a charge of 0. So when you are doing a redox reaction, every single element in the complete ionic equation should have a charge. You should be able to see it. Okay? And now in this reaction, we go back in the complete ionic, And anything that has the same number of coefficients, charge, and the state of matter for that element, in the reactant as well as in the product, if that exists, then we are going to cancel that out. So zinc here, this is zinc solid, and it has 0 charge. This is 2 plus, so we can't cancel that out. This is 2 hydrogens with a +1 charge. This is hydrogen with a 0 charge. Can't cancel that out. You have 2 chlorine with a -1 charge. It's aqueous. In the product, we have 2 chlorine with a negative charge. That is aqueous. So yes, again, we can cancel this out. This is the same reason that we used it in the equation above to cancel out our acetate and ammonia in the reaction. Okay, so now that we have that, we are going to look at the net ionic equation. So the net ionic equation is simply writing out what remains. In this case, what remains is zinc with a 0 charge plus 2 hydrogens, that is aqueous, to produce zinc with a 2 plus charge, that is aqueous, plus hydrogen, that has 0 charge, that is aqueous. So when that happens, in this case, let's look at this a little bit further. And okay, so we are comparing this this zinc to this zinc. And when you compare it, notice that this zinc goes from a 0 to a 2 plus. So if we actually had a number line, and we started off at 0, and we ended up at 2 plus, then are we gaining electrons or are we losing electrons? In this case, we are losing electrons, so we're becoming more positive. So this would be the one that is oxidized. If you look at the hydrogen, on the other hand, hydrogen, we're going from a +1 to a 0 charge. So this is my zinc that I just did it for. And this is oxidized. I'm going to do it for my hydrogen right here. I'm going from a +1, okay, +1 to a 0 charge. So I'm going to put 0 right here to my 0. So I'm moving in this direction. Now I am moving towards the left of my number line. So I'm becoming more negative. So this would be reduced. Okay, that would be reduced. So we can now write our half reactions. Okay, and our half reactions would be red for reduction and oxygen, for oxidation. So in this case, we're going to write it down. We're going to write down for our reduction, which is what I have here. I'm going to label it. I'm going to write down 2 hydrogen. That is aqueous. And I'm going to leave some space, draw my arrow, and then I'm going to write H2, which is a gas. Now we are trying to find out where these electrons are moving. Oxidation, I'm going to do the same thing. I'm going to write down zinc with a 0 charge, that's a solid. Leave some space there, and then write zinc 2 plus, that is aqueous. Okay? And now when I go back to my number line for the reduction, for my hydrogen right here, I'm going from a plus to a minus charge. I'm going to write my minus charge. To a minus charge. So I'm actually gaining 1 electron. But notice, you guys, that I have 2 hydrogens that this is happening to. So it happens 1, and I gain 1 electron. But it happens 1 more time, so this is actually times 2. So that results in 2 electrons that I am actually gaining. So when I am gaining 2 electrons, I'm going to put it right here next to my redox. It's 2 electrons. And what this is saying is that if I have 2 protons plus my 2 electrons would eventually give me a 0 charge. And that's what I'm really going for. So that's why I put it in the reactant here. Oxidation, on the other hand, I've got it. I'm going from 0 to a 2 plus, and I only have 1 zinc at each time. So I'm just losing 2 electrons, but I'm doing it only 1 time because there's 1 zinc on each side. So I'm losing 2 electrons, but only once. And so if that happens, remember that this is 0. I already have 2 protons. So if I want to balance this and make it equal to 0, then I've got to put my 2 electrons here, where I can do 2 plus my 2 protons will give me a 0 charge. So I'm going to actually include this, plus 2 electrons here. The funny thing is that if you do this properly, then if you ever cancel out your electrons, then in the end, you're going to end up with your equation looking exactly like your net ionic equation, if you do it right. And that's what I'm doing, just hypothetically, just canceling everything out. And what do you know? This is the same thing as my net ionic equation. Exact same thing. Okay, so I did do this right. So I'm going to practice one more time with you oxidation reduction. So let's look at this. Let's say that I've gone through and did my balancing equation. I've gone through and I've done my complete ionic equation. And this is what I end up with my net ionic equation. Keep in mind that if an element is by itself, then it will have a charge of 0 on both sides. So this element is by itself, then it has a charge of 0. The bismuth is by itself. It's not bonded to anything. It will have a charge of 0. So now we need to figure out which one's being oxidized and which one's being reduced. So this rubidium, I draw my number line, is going from 0 to 1 plus. So it starts off at 0 and it goes to 1 plus. So it goes this way. That means it is being oxidized. So it's that positive sign. So it's oxidation. And so this is my rubidium. And so now I've got my another number line right here. And I'm going from a 3 plus to all the way to a 0. So I'm going this way. And when I do, this is my bismuth. So I am getting reduced, or I'm gaining electrons. So this would be redox or reduction. Okay? Okay, so now I've got my reduction. Let's figure out how those electrons are actually moving around. So I've got rubidium. And I'm going to copy it as it is for my half reactions. Remember that? My half reactions. I'm going to copy it as it is, leave some space and draw my arrow, and then put my product for rubidium. Okay? And this is for my redox. My oxidation, I'm going to put bismuth, leave some space, and I'm going to put bismuth, the 0 charge, that's a solid. So in this case, I've got my rubidium, and my rubidium is going from a 0 charge to a plus 1. But it does this 3 times. So that actually means that it is losing 3 electrons. Okay, it is the loss of 3 electrons. So where are they going to go, those 3 electrons? Well, you've got rubidium that's got a 0 charge here, and then you've got 3 electrons here. So you've got sort of like 3 protons here. So you're going to add on this side 3 electrons to make it a 0 total to make it equal to, let me put that here, to make it equal to 0, which is this charge here. So this is where I'm going to write plus 3 electrons. Looking at bismuth right here. I've got bismuth. I'm going from a 3 plus charge to a 0 charge. But look, there's no coefficient, so I only do it once. Since I only do it once, I have 3 electrons happening in one shot. So if this side is 0, overall, this is going to be 0. This is where my 3 protons are. So I am going to add 3 electrons on this side to make it a total of 0. So I'm going to do plus 3 electrons there. Okay? Okay, I have one more example here. So let's go ahead and do this. Let's say that I've gone through the balancing equation part and I've written my complete ionic equation. This is my net ionic equation that I have. So remember, if an element is by itself, then it has a charge of 0. If an element is by itself, it has a charge of 0. So I'm comparing aluminum that has a 0 charge all the way to 3 plus. Okay, that's what I'm comparing. And I'm comparing hydrogen that has a plus 1 charge to when it actually forms into hydrogen gas that has a 0 charge. So I'm going to draw my number line then, okay? Draw your number line if this is confusing at first so that you can understand what's going on. You start off with aluminum. This is my aluminum that I start off with a 0 charge. But eventually I end up getting a 3 plus charge. So I'm going from 0 to 3 plus. That means I'm gaining electrons, so this is being oxidized. Okay? On the other hand, I've got another one. I've got my hydrogen that is 1 plus, and it goes all the way to 0. So it goes in the opposite direction. So I've got my hydrogen. Now it is gaining electrons, and so I will say that that is reduced. Okay? Since it's becoming more negative this way, or moving towards the left, then it's gaining electrons. So that's reduced. So if I write this equation down, if I write my half reactions, okay, I am going to write my reduction and then my oxidation. So my reduction in this case will be hydrogen. So I'm going to write down 6 hydrogen plus. That's aqueous. Leave some space, draw your arrow, and 3H2 gas. Okay, I'm going to copy it as it is. And then my oxidation is 2 aluminums. Remember, the aluminum has a 0 charge. That leaves some space, produces 2 aluminum, 3 plus charge, and that is aqueous. My hydrogen gas in the reduction also has a 0 charge. Don't forget, when you write your net ionic equation for your redox equations, everything should have a charge, just as your half reactions. Everything should have a charge. So now let's find out where did those electrons go. So what happened is that you have 6 hydrogens. You have each hydrogen goes from a +1 to 0. So it actually is gaining electrons. But how many times does this actually happen? This actually happens 6 different times. So you're actually gaining 6 different electrons. So you would put it right here, plus 6 electrons. And just to check your math, this 6 means that there are 6 protons plus your 6 electrons. Well, what should they equal? 0 to balance that charge out. Okay. Next one that we have is, if I'm looking at my aluminum goes from a 0 charge to a 3 plus charge. Okay. So each time it loses 3 electrons in this case. But how many times does that happen? That happens 2 times. So if it happens 2 times, that means in total, I am losing a total of 6 electrons that are happening. So where do I put it? In the reactant side or in the product side? So in this case, if I've got 6 protons, right? You're losing 3 electrons. It's happening 2 times. That's how we get our 6 electrons. But if that's happening to your protons and you've got 6 electrons, that should equal out to 0 for the charge of aluminum. So we would actually put it right here. I would put 6 electrons. Keep in mind, if you do this correctly, then once I cancel everything out, if I happen to cancel out my electrons, then I should have 2 aluminums, that's a solid, reacts with 6 hydrogens, that is aqueous, to produce 2 aluminum, 3 plus aqueous, plus 3 hydrogen gas that have a 0 charge. Okay? Keep in mind, if you write your electrons in the correct place, one should be in the reactants, the other one's going to be in the product. It should be the same as your net ionic equation. So after you have canceled those electrons, you should go back to your net ionic equation. So what this is actually saying is that if you have a container, okay, and that container has a line in there. So what that's saying is that your reaction is taking place, is starting off with aluminum here. Aluminum happens to give up its 6 electrons, and what happens is that it allows hydrogen, on the other hand, to gain those 6 electrons. That's what's happening in a battery. In a battery, you're gaining and losing electrons, which is why you have a positive and negative end. You're gaining and losing those electrons. Those electrons are constantly moving around, going from one place to the other. Okay. Hopefully this helped you with understanding net ionic equations and redox equations. I hope it did. I'll talk to you guys later. Bye.